So this is pretty much where we left things off. So we're talking about this whole congruence of time-like geodesics, and we've introduced this point of view here where we select one geodesic as our reference geodesic, and we have a tangent vector field defined on it, and all the other ones. We have a deviation vector that points from the reference geodesic to a neighboring geodesic. And what we've done is to work out an evolution equation for that deviation vector so that the rate of change of the vector along the congruence is going to be, a tensor field multiplying the deviation vector itself. The tensor field itself is, by definition or by calculation, the gradient of the velocity field. And what we've done was to decompose that into irreducible pieces, a trace part, a symmetric trace-free part, and then an antisymmetric part. And now we understand that this thing here represents the rate of expansion of our congruence. So theta is a fractional rate of change of cross-sectional volumes along the congruence. And that's something that, well, we know just by appealing to the fluid analogy that I talked about this morning. And then the shear is something that would deform shapes as opposed to scaling them. And the rotation tensor is something that would, produce a twisting of the word lines. It would produce a deformation, not a deformation, but a rotation of the shapes. And all of that is contained into B. And B in general is going to be just a linear superposition of all of those separate actions coming from each piece separately. And the other thing that we talked about here is the decomposition of the metric into a longitudinal piece and then a transverse piece. And we've talked about the fact that this tensor, and this vector are all purely spatial in the sense of having no component along U. And therefore, in a local Lorentz frame aligned with U, we would find that those tensors only have spatial components, literally spatial components. So any questions about any of this before we move on?
So,
yep.
In the context of cosmology, would theta be a scale factor?
Hold on for 1 minute. I'll talk about cosmology in a minute. So I'll do an example of all this involving cosmology. And in fact, theta is not a scale factor, it's the Hubble parameter, right? The rate of change of the scale factor up to a numerical factor. But we'll do that in just a second. Before I erase it, don't forget that you have a homework due now in 2 weeks' time. And those are the problems. Okay, so I'm going to keep developing this. And one thing I want to talk about is situations where the rotation tensor would happen to vanish. And I want to work out the consequences of this, and all of this is known as Frobenius theorem. Let me move this up. So let me state it first. The theorem states that if, no, I'll say it differently. The statement is that the congruence of time-like geodesics is hypersurface orthogonal something that I'll define in just a second, if and only if the rotation tensor happens to vanish. What does it mean? Well, we're given a congruence, and I've drawn it a number of times already. The congruence will be hypersurface orthogonal if, well, it pretty much says itself, right? If, you can construct a whole sequence of hypersurfaces such that at any point here, the tangent vector field to the congruence happens to be a normal vector to those hypersurfaces. So the construction is such that, so you have hypersurface sigma 1, hypersurface sigma 2, hypersurface sigma 3. You have a whole stack of hypersurfaces at every point in this domain here, in this open region in which the congruence is defined. And at every point, you have that the normal to the hypersurface is aligned with U. So what that means is that we have a sequence, we have a family of hypersurfaces such that the normal to the hypersurface is everywhere aligned with the tangent vector field. So there are lots of situations where this is true. There are lots more situations where this would not be true, so that you would not be able to find a whole stack of hypersurfaces like this that would satisfy the property. So most congruences, will not have this property of being hypersurface orthogonal. The ones that do, though, are the ones for which the rotation tensor vanishes. So I'm not going to prove this in all generality, but I just want to give you an idea of how it works. In the book, I do a little bit more than that, but even there, I don't prove it in all generality, because if you look up a proof in in differential geometry books, it turns out to be involved. You have to rely on forms. It's a fairly elaborate thing. So I'm not going to give you a full proof, but at least I'm going to show you the basic reasoning behind the connection between this condition over here and this notion of hypersurface orthogonality. So is it clear what it means? Yep. For this one, I'm going to restrict it to geodesic congruences, but there's an alternative statement of the theorem where the nature of the curves is irrelevant, so it could be non-geodesic curves. So I'll just say a few words about that. Okay, so in general, the condition is that this completely antisymmetric tensor field has to vanish. So the condition in general for Frobenius theorem for any type of curve, geodesics or non-geodesic, would be that the fully antisymmetrized product of U with the gradient of U vanishes. And a statement then of the theorem would be that the congruence of curves in that case would be hypersurface orthogonal if and only if this condition is satisfied. When we restrict it to geodesics, this condition boils down to that. So in the book, I show you a bit more about this. I actually, sort of prove that in one direction, not the other. So what I do in the book is to prove that if you have hypersurface orthogonality, then you have that. What I don't prove is the converse, because that's the hard part. So I did the easy part in the book. So if you have that, you have that. And then for geodesics, if you have that, you have that. And that, the converse to that is easy. The converse to this, from here to there, is much harder. And for that, you have to go to, differential geometry books, or I think Wald in one of his appendices has a proof of this. But again, that's the harder part of the statement. So in the book, you can read about this version of the theorem. But here I'll just focus on that one, and that turns out to be pretty easy to understand. Okay. So we're talking about hypersurfaces, and of course, in the next chapter of the book, I'm going to be saying a lot more about hypersurfaces, but I'll just introduce some key ideas here that will bring out this connection. So the first question I need to ask here is how would we describe a hypersurface in space-time? And I'll give a lot more information about this in chapter 3, but right now I'll just say that so first of all, what's a hypersurface? A hypersurface is just something, it's just a submanifold of the space-time manifold that has one fewer dimension. So it's a codimension one. surface, so we would be talking about a three-dimensional surface in 4-dimensional space. That's what I mean by a hypersurface. And there's some fine print that's associated with that. It has to be a proper submanifold of the full manifold. It has to be, it has to be smooth. It has to be its own manifold. Anyway, so there are all sorts of things, but it's pretty clear what we mean in 4-dimensional space-time. In the case of a time-like congruence like this, we would be talking about a whole bunch of spatial surfaces. And those spatial surfaces are such that they're supposed to be everywhere orthogonal to that congruence of time-like geodesics. So in flat Minkowski space, I could consider the congruence of time-like geodesics that consists of just curves of constant spatial coordinates, right? They just move in time. Those are orbits of the time-like killing vector. That's a very nice congruence. And the hypersurface orthogonal to that will be the hypersurface of constant time in Minkowski space-time. And that's an example of a congruence that turns out to be hypersurface orthogonal. It's a bit of a trivial example, but it applies anyway. Okay, so a hypersurface well, a hypersurface can be described in any number of ways, but one way to do it would be to put a restriction on the space-time coordinates. So a hypersurface is described by a statement like some function that I like to call capital phi of the space-time coordinates is going to be equal to a constant. So, as a quick example of this, if I'm talking about a two-dimensional surface in three-dimensional space, and if I take that surface to be a two-sphere, then I would say that, say a two-sphere of, if I'm talking about a two-sphere in flat 3D, the kind of conditions I would put would be to say, for example, that my function phi would be x squared plus y squared plus z squared, and that would be equal to some constant r squared. That's the sort of thing I'm talking about. Some restriction on the coordinates that tells us that, well, we're considering a surface in the higher dimensional spacetime. So other than that, I'm not going to say anything more, but that's just a statement that, sigma 1 over here would be described by the function being equal to, say, 1. This would be the function being equal to 2. This would be the function being equal to 3, and so on and so forth. So phi is equal to a constant on each hypersurface, and then the constant, of course, would depend on which hypersurface I'm talking about. So a specific constant to each one. Okay, so that's the way we describe our hypersurfaces for the purpose of this argument. Now the question is, we were talking about the normal vector to the hypersurfaces, and I want to decide whether the normal is going to be aligned with the U field, and I need to construct the normal. Well, you may remember this from elementary calculus or whatever. But the point is that I can generate the normal to a hypersurface by just calculating the gradient of that function. And the idea here is that, well, if I evaluate the gradient of a function like this, the function phi, well, the vector gradient, or the gradient vector, say, is not going to be tangent to so because the function doesn't change as I move within the hypersurface, that vector has to be directed in directions away from the surface, which is what we mean by the normal direction. So I'm saying two things. I'm saying first that because the function doesn't change as I move within the surface, the gradient vector cannot point within the surface. And because the function changes only as I go away from the surface, as I move from one to the other, well, the gradient vector has to point in that direction, and that's the direction of the normal vector. So all I'm saying here is that the normal to the hypersurface sometimes I call it n, is going to be proportional to the gradient of that function phi, because the function only changes as you go away from the hypersurface in the normal direction. Yep?
I might have forgotten this. So this is normal with respect to some kind of Riemannian metric, and we are talking also about Lorentzian metric.
Well, this notion of a normal as defined as a gradient doesn't refer to the metric at all. Of course, if I want to convert it to a vector, then I would need the metric to raise the index. But at this stage, I'm just defining it as a one form, and that doesn't require a metric. So what I should have said is that the normal one form is the gradient one form of that scalar function. Other questions about that? Okay. So the reason why I say proportional to is that usually we like the normal vector to be normalized. So what I'm going to do is to put in a factor in front just to normalize it. So I'm going to say that the normal vector is going to be, I'm going to put in a minus sign. I'm going to put in a factor in front, and then I'm going to say that it's proportional to the gradient function. So mu is a scalar field. It's a scalar function for normalization. And this is normalized. Now you're all asking me, well, why the minus sign? Well, the minus sign is there just because of, well, the fact that we are in fact dealing with the Lorentzian manifold, so that there's, annoying minus sign in a metric that sometimes we have to consider. So the reason why I'm incorporating a minus sign here is because I've chosen my function phi to increase forward in time, and that's a sensible convention. When I convert this one form into a vector, I'm introducing another minus sign, right? Because it's a time-like one form. So basically, this minus sign is what I need in order to make sure that the vector associated with that, n alpha with the index up, is a future pointing vector. If I didn't have this minus sign and I were to raise the index, suppose that this is so suppose I'm working in a local Lorentz frame, and suppose that I pick the scalar field phi to be suppose that I pick each hypersurface here to be a surface of constant t, then after raising the index, if I didn't have this minus sign, I would find that n with the index up would be negative instead of positive, so it would be past pointing as opposed to future pointing. So the minus sign basically means that the vector is future pointing.
Assume that mu is positive.
Yeah, I'm assuming that mu is positive. So not a big deal, but I like to see where the minus signs are when I do things like that, so I put it in explicitly. Okay, so what do we have? So now we have our description of the hypersurface, the family of hypersurfaces. We have the normal vector. So the point is that the congruence is hypersurface orthogonal. When U agrees with N, and that means that U alpha with the index down is proportional to a gradient. Right? So mathematically, that's what it means for a congruence to be hypersurface orthogonal. I can claim that everywhere along the congruence, we're going to have U being proportional to a gradient. So let's see the consequences of that. the gradient of u, which is our tensor field B, is going to be phi differentiated twice. Then we're going to have phi differentiated once, and then mu differentiated once. Omega alpha is going to be the antisymmetric part of this. Which means that the first term is going to drop out because the first term is fully symmetric, right? So we know that two covariant derivatives acting on a scalar commute. It wouldn't be true on a vector, it wouldn't be true on a tensor, but on a scalar it does commute. So this is a symmetric tensor, which means that this antisymmetric combination is just going to be involving this, and I'll write it down explicitly. We have minus a half. The half comes from the antisymmetrization bracket here. So we get d alpha phi d mu, d beta mu minus d alpha mu d beta phi. All right. I'm going to write it slightly differently. Just recalling this equality over here, I'm going to get 1/2, and this is u alpha d beta mu minus d alpha mu u beta. All right. Well, one thing we know about omega is that it has to be orthogonal to u. So let's build it in. Oh yes, sorry. There was this factor of mu missing, 1/2 mu. Yeah, I got rid of a minus sign here. Yeah, thank you. Okay, so one property I have to have is that omega is a purely spatial tensor. And what that gives me from that equation, I get the 1/2 mu. If I multiply by u alpha, I get -1 from over here. And from over here, I get minus u beta times the rate of change of mu along u. The rate of change of mu along u. And that has to be equal to 0. And what that means is that mu as a scalar field can vary, but it can only vary in the direction of u. That's what this equation here means. So what we have here, and we have to have that because, it's something that we had from the start, that omega was a purely spatial tensor, like B, like everything else. For all of this to be consistent, for all of this to work out, we can allow mu to vary, but it can only vary also in the direction of the normal or in the direction of the velocity field u. And if that's true, well, we find that all components of omega actually have to vanish. Because if grad mu has to be proportional to u, then this is proportional to u, this is proportional to u, and the two terms are just identical and they cancel out. Right? So as a consequence, we have that. So the chain here, the chain of logic is, so we claim we have, we state that we have hypersurface orthogonality, so we impose that condition. That gives us this automatically. The notion that the normal vector, which we have here, is aligned with the time-like vector field of the congruence. And once we have that, it's just a simple computation that, that tells us that omega, as defined previously, has to vanish. It's just a direct consequence. So what we have here is that if we have that, then we have that. And with a little bit more work, I think I could probably go the other way and show that if we have that, we must have this. I'm not going to try that. You can try that. Why not? That's a nice challenge. I don't think that's too hard to do. You can show that if this is true, then this has to be true. And then we have the if and only if part of the theorem, which I wrote down before. So that's the idea. So if we have a congruence that is hypersurface orthogonal, then we have that condition holding. And if we have this condition holding, then the claim is that there's going to be a stack of surfaces that we can go and find that will be everywhere orthogonal to that congruence. And in more general terms, you can also, instead of this, you can connect this condition of hypersurface orthogonality to this more general statement. And it's the same thing, except now formulated in more general terms, where the vector field here doesn't have to be satisfying the geodesic equation. That's a more general version of that. All right? So you may ask now, why do I care about this? Why do I care about hypersurface orthogonal congruences? You'll find out. We will care about this. When we talk about cosmology, well, we'll find that that's a case where the cosmological fluid is an example of a congruence of, a hypersurface orthogonal congruence, and the hypersurfaces are, the hypersurfaces of constant time of standard cosmology. So each hypersurface that's orthogonal to the flow of the congruence is one of those, space-like hypersurface that are, t equal constant slices in cosmological spacetimes. So we'll see that a little bit more in a moment. Any questions about this? Any mysteries or little gaps? Yep.
The second condition is intuitive to me. So the first one, no rotation, I can't have any intuition why.
Which one is intuitive?
The condition of, so in order to have the hypersurface orthogonal,
This one?
why the rotation part is 0? You said you wouldn't prove it, but is there any way to have some intuition? Why not shear being 0?
Why rotation? Why is the rotation singled out here? I guess I have to admit that I never really came up with an intuitive understanding of this. I just don't have a good answer. I think the reason why it turns out to be the antisymmetric part of the gradient field really is bringing out, a connection with forms. And when you have forms, you have when you have hypersurfaces, you tend to have forms, and it all plays out this way. But that's not a very satisfying, it's not even an explanation. That's certainly not a very satisfying anything. So why it turns out that it's physically the rotation that matters here, I wish I had a good answer. I just don't. Maybe one day I will. Maybe one day you'll give me a good way to thinking to think about this. Other questions? Okay. Well, now I'm going to do something cute. I'm going to derive one of my favorite equations in differential geometry and GR, and I'm going to prove the focusing theorem. So, next topic, continuation of what I'm talking about here, is Ray-Chowdhury's equation. Ray-Chowdhury was, I'm not sure if he, I shouldn't say anything. Ray Chowdhury is or was a famous Indian relativist who did a lot of work on mathematical cosmology, and he derived what I consider to be one of the most beautiful equations of differential geometry. And, well, I want to tell you something about it. So when we were decomposing the gradient field into irreducible pieces, we were just basically doing kinematics. There was really nothing dynamical about anything. And if you recall our discussion of fluid mechanics this morning, I never wrote down Euler's equation that tells us what the acceleration of each fluid element was. All I said was, let's describe the relative velocity between two neighboring elements. And basically, the rest of it was just playing with kinematics, just elaborating on the kinematics of the situation. Here, it's the same thing also. So when I write this down, I'm really talking about, I'm really describing the relative velocity of two neighboring geodesics, of this geodesics relative to the neighboring one. And basically, again, we're at the level of kinematics where we don't make any statement as to what is causing an acceleration between relative geodesics. When we were doing the geodesic deviation equation, we were, in fact, doing dynamics in that sense. We were making a statement about acceleration. Here, we haven't reached that stage yet. We're only making a statement about relative velocities, and that's pure kinematics. Ray Chowdhury's equation is really asking, doing the next step, which is to go to the dynamics level. And in principle, so the idea would be to derive evolution equations for each of those irreducible quantities that characterize the gradient field. So you can derive an evolution equations for theta, you can derive an evolution equation for the shear and for the rotation tensors. And in the book, in the text, I only do it for theta. That's the simplest thing to do. In the problems at the end of the chapter, I actually ask you to go through the evolution equations for the shear and rotation, and I haven't decided yet whether I'll ask you to do that for real or not. But in any case, the idea is to go one step further from this and access the dynamics of neighboring geodesics. So when we ask, so I'm going to be deriving an evolution equation for the expansion. When we talk about the expansion, we're talking about the first rate of change of those cross-sectional volumes. So we're really talking about the rate of expansion. What I want to work out is the rate of that rate. So the second rate, basically, of expansion or contraction. So that's where we're going with this. And the first step is going to be to just get started with an evolution equation for B itself. So I'm going to start with B. I'm going to do it general for a little while, and then I'll specialize to just an equation for theta itself. So let's work out an evolution equation for B. And that's essentially a little bit more, it's a little bit more general than what we did last week for the geodesic deviation equation. We just do it, in a way that incorporates a few more things. So what do I mean by an evolution equation for B alpha beta? So I really want to work out the covariant derivative of that tensor along the congruence. So I can write it in this form, or I can write it in this form. Or I can write it in fully explicit form by just remembering that this is the velocity gradient field in a congruence. So I want to work this out. What I'm going to do is to apply the usual trick of switching the ordering of those derivatives, and I'll bring out the Riemann tensor to compensate for that. So what I'm going to do is to rewrite this as U alpha semicolon mu beta. And what I have to do to compensate for this is to introduce a Riemann tensor. And the indices work out that we place a nu here. That's a dummy index. Then we have this sequence of indices. And then we have U nu multiplying that. And then we have U mu coming along for the ride. Good. I have exactly the same equation is in the book. So I'm going through the steps we went through before when we did geodesic deviation. So here what I'm going to do is to multiply this by here. But what I'm going to do is to factorize the, propagate the derivatives. So I'm going to write the first term as all of this differentiated with respect to beta. And then I'm going to make up for the difference. And the difference is going to be minus u alpha semicolon mu, u mu semicolon beta. Right? So all of this is just this multiplying that. And here I've thrown in a u mu, this u mu into the derivative, and then I make up for the difference, and that's what I get. So this and that account for this, and then what we have on top of that is, I guess I want to write it in this form. I'll switch the ordering of those two indices over here. So I have alpha nu beta mu multiplying u nu u mu. All right. This is 0. That's why I did this. By virtue of the geodesic equation, we get rid of the first term. This we recognize, that's our b. And this we recognize again, that's also our b. Right? So in the end, I end up with a fairly clean-looking equation where I have minus b alpha mu, b mu beta, plus Riemann tensor alpha mu beta nu u mu u nu. Here I change a mu into a nu. It has no impact because here we have the symmetric combination between nu and mu. So I can symmetrize here without changing anything. Or you can view this as just a relabeling of dummy indices. It doesn't change anything either way. Okay, so that's my evolution equation for B. And what I can do from now on is to apply this decomposition into irreducible pieces, and I can infer from that an evolution equation separately for theta, sigma, and omega. Excuse me. So what I'm going to do is to just do a third of that program, and I'm just going to work out an evolution equation for theta by taking the trace of this equation. So if I take the trace, then we end up with, well, if I call the trace b, but we know that the trace stands for theta, on the left-hand side we end up with db d theta. So here I don't need to distinguish between covariant derivative or ordinary derivative, because after taking the trace, my tensor becomes a scalar. And then I take the trace on the right-hand side, and I get this product of b's. And here it's important to notice that here we have alpha mu, here we have mu alpha after taking the trace, so that it's not the same ordering in each term. And then taking the trace of this term over here, I'm taking the trace of the Riemann tensor that gives me the Ricci tensor, and we get the Ricci tensor multiplied by mu and nu. Okay, so now I just need to do a couple more steps. I just want to re-express this in terms of the simpler quantities, and after that I'll just make the switch, call this theta, because that's what the trace of b is, and we'll see what we get. So let me work out the two b's, the product of the two b's, and see what this is. So I'm just going to plug in what B stands for after the decomposition. So first of all, we get a third H alpha mu theta plus sigma alpha mu plus omega alpha mu. And then I multiply this by a third H mu alpha theta plus sigma mu alpha plus omega mu alpha. And you'd think, oh no, that's terrible. I'm going to have to do each multiplication, and there's going to be 9 terms in that. It's going to be a big mess. But in fact, it's not, because each piece here is irreducible, and therefore it means that they don't interfere with one another. So first, let's multiply this by that. What we're getting out of it, so we're getting a factor of 1/9, but we're also getting a factor of 3 by taking the trace of h. Sorry, I'm doing two things. I'm taking the product of h times h, but we know that h has this property of being a projection operator, which means that acting twice with h gives us another h back. And this h will have, well, it's going to be the trace of h. Anyway, you can fill in the gaps, but what I'm saying here is that from multiplying this term by that term, you get 1/3, you get 1/3, and you get a 3 by multiplying the h's. So you get the 1/3 back, and then you get a theta squared. So that's the first term after multiplying. When you multiply this by that, well, multiplying sigma by h means let's take the trace of sigma. But sigma is trace-free. So that term doesn't interfere with this term. Same story here, right? Multiplying omega by h means taking the trace of omega, but omega is antisymmetric. It's also trace-free, and there's no interference there also. So you keep going like that. Now we're down to this multiplying that, that's 0. This multiplying that gives me a sigma squared term. And here I can switch the indices because that's a symmetric tensor. So I'm writing it in this form as opposed to that form. No problem here. Multiply sigma by omega, we have a symmetric tensor multiplying an antisymmetric tensor. That's always 0, so no interference here. So you see everything simplifies very nicely. Then we get omega times h, that's 0, omega times sigma, that's still 0, and finally we get omega times omega. And here I'm also going to switch the two indices, but now we're dealing with an antisymmetric thing. So by switching, I have to introduce a minus sign. So that's the outcome of multiplying b times b. So instead of 9 terms, because of this decomposition, we still get 3 terms. So we're done. We plug that into the original result. We get that the rate of change of theta with respect to proper time along the congruence is going to be minus all of this. So it's going to be minus 1/3 minus the squared theta, the squared sigma, sorry, plus the squared omega, and then plus the Ricci term. And that's the equation known after Raychowdhury's equation. Okay, just to clarify what this all means. Theta is the rate of expansion. And as I said repeatedly, it's the fractional rate of change of cross-sectional volumes as you follow the congruence. So theta, we call it the expansion, but it's really the rate of expansion, the first rate of expansion. If I differentiate that with respect to time, I'm constructing the second rate of expansion. So it's really the second derivative of the rate of expansion. Okay? And what I have is an equation for that second rate expressed in terms of all sorts of things involving, the expansion itself squared, the sheared squared, the rotation squared, and then something that comes directly from the Ricci tensor, which, if we apply the Einstein field equations, would be related directly in terms of the energy momentum tensor of the matter distribution. All right? So it doesn't look like much looking at this right now, but in fact there's a lot of wonderful things hidden here. And mostly that's because from here I can prove a focusing theorem that basically makes the statement that if you have matter in your space-time, and if that matter satisfies reasonable energy conditions, then if you have geodesics that are focusing, they'll focus more rapidly in the future. If you have an expanding congruence, it will expand less rapidly in the future. So that basically matter has the action of focusing, time-like geodesics together. So basically, that's a statement that gravity acts in an attractive manner. So gravity is an attractive force. And one manifestation of this attraction is that, well, if geodesics are converging already, they'll converge faster so that they'll get closer together. If geodesics are diverging away from one another, they will diverge less rapidly in the future. They will, again, get closer together. That's the content of the focusing theorem, and the focusing theorem is basically based on this. In fact, it's very simple to prove the focusing theorem. It's staring right at you right now. So let's look at this equation. When we deal with space-time vectors or tensors, and we take an inner product between, say, a time-like vector. So suppose I give you a vector in space-time, and I ask you to calculate the inner product of that vector with itself, its norm. Well, you can get a negative result or you can get a positive result because we don't have a positive definite metric. We have, this minus sign in front of the time part of the metric, which means that if we're dealing with a time-like vector, we're going to get a negative norm. If we get, if we're given a space-like vector, we're going to get a positive norm. So in general, in space-time, when you're dealing with a squared quantity like this, there's no guarantee that the outcome will be positive, because it really depends on the nature of the tensor that you're squaring. If that tensor has a time-like component, then it could be that this time-like component will win and will produce an inner product of that tensor that's going to be negative instead of being positive. This won't happen here. Remember, all of our tensors here, B, sigma, H, omega, are all purely spatial tensors. So there's a local Lorentz frame in which there's no time entry at all in those tensors. And therefore, when you square it, the only thing that shows up are positive values and positive spatial metric. And therefore, because we're dealing with spatial tensors, this is positive or at least non-negative. This is positive or at least non-negative. So theta squared, that's always going to be positive or at least non-negative. Sigma squared is always going to be non-negative. And omega squared is always going to be non-negative because these tensors are spatial. They have no time entry. So that's guaranteed. What I want to prove is that this quantity on the left-hand side is always negative. And it's looking good, except for a couple of things. It's looking good here. I have a minus sign, and the rest of it is non-negative. It's looking good here because, again, I have something non-negative, and I have the minus sign. But here, I'm screwed. This is positive, and I have a plus sign, which means that there will be situations where this will win over all of that, and I wouldn't be able to guarantee that the left-hand side is negative. So that's a bit of a problem. The other piece right here is something that also could be a problem. So I'm talking here about the eigenvalue of the Ricci tensor along the direction of u, or the projection of the Ricci tensor in the direction of u, and who's to say that this is guaranteed to be positive, or who's to say that this couldn't be negative? So I have to put in some conditions on that. So the focusing theorem will come out if I kill this, and if I put restrictions on that to make sure that they don't produce anything that's positive on the right-hand side. So why do we care about hypersurface orthogonal congruences? Because I want to kill this term. That's why. Why do we care about energy conditions? Because I want to control this term as well. So last week I asked you to review that section in the book on energy conditions. I won't go through that, but I'll just impose a condition on this that guarantees that this is always positive, the same way that this is, the same way that that is. And now I realize that I made a mistake somewhere because I really wanted this to be a negative sign. Where did I go wrong? Oh, that was a plus, right? Because I was working on a one form, not a vector. So this should have been a plus sign. So now this is a minus sign, minus, minus. Sorry about that. So I do have a negative sign here, and basically I want to impose conditions on this so that it's always positive, and then I'm going to kill this, and then everything on the right-hand side is going to be negative, and then I have my focusing theorem that says that this is always negative. So you had a question?
Yeah, just if you don't get rid of omega, would that respond to like a centrifugal force, which is?
It would be analogous to centrifugal force. Yeah, the twisting of the word lines would basically prevent them from converging beyond a certain limit. So yeah, it's like a repulsive centrifugal term in a bunch of other terms on the right-hand side that would have the opposite sign. Okay, so let me just write down what the focusing theorem is, and then I'll comment on this extra condition that we have to put in that the congruence has to be hypersurface orthogonal. So we're going to let the congruence be hypersurface orthogonal. Meaning that omega is going to be declared to be 0 for our congruence. And we're going to impose what's known as the strong energy condition. Namely, that the component of the Ricci tensor along U cannot be negative. So that's a statement that positive Ricci curvature is going to be, a requirement here in our space-time. It's really a condition on the Ricci tensor, but because the Ricci tensor is going to be related to the stress energy tensor by the Einstein field equations, you can translate this into a condition on T mu nu instead. And that's where the name strong energy condition comes in, because now it's really a restriction on whatever matter fields live in that space-time. So another way of writing this using the Einstein field equations is that this combination of T mu nu and its trace dotted with U also has to be positive. And in the book, I give you a bit more discussion on this, and I show you how that relates to the sign of the energy density, the sign of the pressures, and various things like that. And the expectation is that most forms of matter in the classical world will be satisfying this condition. Fundamentally, we're really putting a condition on the Ricci tensor, and to use the Einstein field equations in that discussion is not wrong, but it's not essential. So instead of calling it a strong energy condition, I'd rather focus on this condition right here and call it the Ricci condition or whatever. But in the literature, that's what people do. But that's just to the basic point here is that none of what I've done here relies on the Einstein field equations. It's purely something that depends on differential geometry. The only link to the Einstein field equations comes in when you try to translate this requirement into this requirement that forces you to use the Einstein field equations. But it's really not essential. What's essential is this, and if we have that, then we have a specialized form for Raychaudhuri's equation, where the right-hand side is declared to be non-positive, and therefore we have the statement that theta will decrease in time. So what does it mean? Well, my congruence could be expanding, and that would mean that theta is actually positive. If I have congruences where the geodesics are all flying off of each other, diverging away from one another, that means that theta is positive, and there's nothing wrong with that. That's an example of an expanding universe. What the theorem says, though, under the conditions of the theorem, is that even though my congruence is expanding, the rate at which it expands will decrease in time, will slow down. So this rate of divergence, this rate of expansion, will actually decrease in time because the rate, d theta, the change in theta, the change in the rate of expansion is negative, therefore the expansion will slow down. So if initially the congruence is expanding, if you have an initial divergence, the divergence will decrease in time. And it's decreasing in time because the matter and the shear and the expansion itself are all acting as to focus the geodesics, and they bring them essentially closer together. So initially they're expanding, but they're forced to come closer together by the focusing action of the matter, the shear, and the expansion itself. Right?
If we have no curvature in flat space-time, it sort of seems intuitive that you can have like a positive or negative theta, but that the rate of change of it should be constant. But that doesn't seem to be the case here. Because we can still, just because our alpha theta is zero.
Well, in flat space-time, you have this, so it's a very special case, right? So how does it work? I think, so in flat space-time, you have, you can have diverging straight lines like this. You have a velocity field, and you have a velocity gradient. But I think you have a velocity gradient that's such that the point is that this should be zero for flat space-time, and I think the point is that, well, you can't have cancellation between these two things.
But isn't the combination of d theta over d tau and the first term, theta squared over 3, isn't this combination give you a doubled up over A? Or the second Friedmann equation?
If we're talking about cosmology, but now we're talking about flat space-time, right?
No, but I'm thinking if you had the universe where there was nothing in it, right?
Right.
And there was no shear, then you would have the second derivative of A vanishing, being zero. So what counts is the second derivative of A, not the derivative of tau. Of theta. Because if you said that theta is A dot over A, so then its derivative has two terms.
Yeah.
And then the first term there cancels one of them and would give you the second Friedmann, a doubled up over A.
Is it because we're taking the derivative with respect to tau and not t? Maybe some time.
There's a thing about this. I think I'll think about this, and I'll get back to you next week because it's a really puzzling question. I should have thought about this before, but it never occurred to me before. But yeah, there must be some simple resolution of this. But off the top of my head, I can't see it. Okay. So anyway, so in the general setting, then if you have an expanding congruence, then it will expand less rapidly in the future because of the focusing action of each of these three things separately. If the congruence is initially converging, so that can happen too, then the statement is that, well, it will keep on converging but faster. Because theta is initially negative, you're going to force it to be even more negative in the future, and that means that the rate of contraction will even increase in the future. And that's interesting because that signals the formation. So basically, you're going to produce a sort of catastrophic type event where, if you're initially converging, so the word lines are already approaching each other, they keep on doing that, but faster and faster. And at some point, even though all along you were trying to avoid crossing points, you can't avoid them any longer. And in fact, when you have an expansion that's initially negative, you will have crossing points forming at some finite time in the future. And in the book, I give you a bit more information about this. So within a certain amount of proper time, you will have geodesics starting to cross one another, and that's called formation of caustics. So when geodesics start to cross each other, you have the formation of caustics, which are crossing points, and those are places where theta is driven to minus infinity. So it's a very bad singularity of the congruence. We don't want to deal with that because that's breaking. That's the signal that our whole formalism is breaking down. But the point is that you cannot avoid those situations if theta is initially negative and the focusing theorem is active. So if all the conditions are met, if the congruence is initially contracting, it will keep on contracting until all the geodesics start crossing, and we get caustics, and we get a bad singularity of the congruence. So the focusing theorem is pretty powerful. And it's often a way to, so first of all, let me mention two things. So I mentioned the condition of hypersurface orthogonality. So that's certainly a very strong condition to be put on the congruence because, in the general case, that condition will not be satisfied. And if you don't have that, then you can't control the right-hand side. And there's really no, conclusion to be drawn by just staring at Ray-Chowdhury's equation. So in the timelike case, that turns out to be very restrictive, although in the case of cosmology, it's not really restrictive. It's just part of the symmetry assumption we would place on the universe. And I'll say a few things about that in a moment. When we consider the null case, then it turns out that this restriction is not very serious at all. And that's something, so next week we're going to turn to the null case. So this was basically just a warm-up exercise to go up to the null situation where instead of time-like geodesics, we're considering null geodesics. And the null case has all sorts of interesting subtleties and everything. But it turns out that there's going to be a Ray-Chowdhury's equation that will also apply to the null case. But in that case, this condition over here is not a very strong restriction. So that when we actually apply it to things like black holes, it's not going to be something that is going to be very strange. It's not something that's going to be a very strong restriction on the congruences. So an example is this. So ultimately, we're going to be applying all of this to event horizons. Well, an event horizon is an example of a null hypersurface, which is generated by null rays, null geodesics that are purely tangent, that are always tangent to that null hypersurface. So null hypersurfaces are always generated by null geodesics that are tangent to that surface. And the congruence of null geodesics on the null hypersurface is a congruence that's hypersurface orthogonal. So in that context, it's very natural because we're given the hypersurface and we're given the null generators. It's very natural to have this condition satisfied. So it comes naturally, and therefore it's not seen as a very important restriction on the whole thing. Let me mention another aspect of this. Sometimes you're given a space-time that has all sorts of strange properties. And you ask yourself, what did I need to put in that space-time to give me those properties? And sometimes the answer is I had to put in an awful lot of negative energy to make this happen. An example is a wormhole, right? And in the first, in the homework problem, I'll ask you to work out the energy conditions for an example of a wormhole space-time, traversable wormhole space-time. Well, what's an example of a wormhole space-time? It's the usual thing where you have, two flat sheets. And there's a mouth relating this part of the universe to the other part of the universe. So that gives you a shortcut to go from over here, down there, over there. And usually it's assumed that there would be a long cut, going along this way that would take you from here to there, but this is the shortcut through the wormhole. So that's an example of a space-time that has all sorts of funny properties, including a wormhole in it, right? Traversable wormhole in it. But when you look at this and you think about all of this, it's pretty clear that in order to produce this, you had to violate the strong energy condition. Well, think about this. Suppose that I give you a congruence of observers falling through the wormhole coming from all possible directions. So we have observers coming from all directions falling down the wormhole. So they're all converging. Under the conditions of the focusing theorem, they should keep on converging until they all collide with one another. That would be the caustic formation that we talked about. But it doesn't happen. They all come back. And after going through the wormhole, they all start diverging away from one another again. So what do you need to produce this converging behavior that turns into a diverging behavior? Well, you need to violate the conditions of the focusing theorem because you're violating the theorem itself. Well, you can think about this. You can do the work. You can prove yourself that, well, those observers are, in fact, hypersurface orthogonal. You can work this out. So that the only place that you have to actually produce a violation is through the Ricci term over here. And the conclusion is that, well, in order to keep the wormhole there, you have to put in some matter in here. And that matter has to violate this energy condition. Because if it did not violate this energy condition, well, the focusing theorem would say that those observers would all have to run into one another. Because they don't, this condition has to be violated. And without doing any calculations at all, except taking my word that there's nothing wrong with this, without doing any calculations like that, just thinking in terms of pictures, you know that this is an example of a space-time where energy conditions are violated, which means that in practice you would have to put in a lot of negative energy in order to keep the wormhole open. And that's kind of nice, right? I mean, you don't have to do any work. You have already a lot of intuition as to the nature of the space-time. And there are lots of other examples like this. In my career I've encountered I don't know how many examples like this where you stare at a space-time diagram and you see some funny things going on and you say, aha, there must be some negative energy there because otherwise geodesics would not behave this way. And sometimes somebody who's not, remembering all of this would say, how do you know that? And you say, oh, I'm just clever. I just know these things. Well, it just comes out of a, simple reasoning like this, where if you see, diverging, converging behavior leading to diverging behavior, you know that you're violating something, and therefore you need a strong violation of the energy condition in order to make that happen. All right, so I want to talk about cosmology. So I think I have about, well, I'll just set this up. I may not complete it. But any questions about any of this before? Yep.
So then this would also be the case in like an accelerating universe?
In an accelerating universe, yep, that's right. In an accelerating universe, absolutely. So that's a classic example. You have the cosmological fluid that's expanding because the universe is expanding, but it's speeding up in its expansion, right? That's our universe today, apparently. From Ray Chowdhury's equation, from the focusing theorem, we know that the energy content of the universe has to violate the strong energy condition. Now, violating the strong energy condition is not necessarily saying that you have to have negative energy in it, and we know that our universe doesn't seem to have negative energy in it. But it's enough for the pressure to be as large as the energy density to violate this condition, and that seems to be what's causing it. So the cosmological constant is, if you think of the cosmological constant as something with a density and pressure with a specific equation of state, well, it's an equation of state where P is negative the energy density. And that's enough to produce a violation of a strong energy condition and to produce a ever-expanding universe, accelerating universe. Yeah, very good example.
But the difference with the wormhole that seems people believe in one and don't believe in the other. But I don't know what the case is.
I don't know what people believe in, right? So. For the wormhole, in order to actually make this happen, you would actually need negative energy density inside the wormhole. there's some exotic models out there where people claim that you don't need exotic matter to maintain a wormhole, but in fact, well, I think for most wormhole solutions, you do. And you know, I can believe in I can sort of believe in, well, I can sort of see, well, I know that, you know, a cosmological constant will lead to a violation of this, and I can sort of accept that. Accepting the existence of macroscopic amounts of negative energy is something I have a hard, you know, problem with. I know that quantum mechanically I can create quantum states, like the Casimir energy, for example, that leads to microscopic amounts of negative energy. So that I can, you know, that I can accept. That's part of quantum mechanics. That certainly is valid. You have all sorts of quantum states in quantum field theory that have, you know, little pockets of negative energy surrounded by, you know, larger regions of positive energy. So so you can, you know, find negative energy pockets in quantum mechanics. But somehow you would have to build this up into, you know, for a traversable wormhole, you would have to build this up into a macroscopic amount of negative energy. That's a little bit harder to accept. I mean, to me, anyway. But still, it's fun to think about these things. Other questions? OK, so let me just tell you, and I think I can do this fairly briefly, how to do cosmology without thinking of FRW metrics or even coordinates. Yeah, I'll get it started. So, normally when you study cosmology and when you did it, well, the first thing you do is to, well, you state the postulates of the standard cosmological model, right? You have a homogeneous spacetime, you have, you know, a metric, so you write down a metric, you introduce a scale factor, and then you talk about the cosmological fluid, the fact that, you know, it's a fluid that's uniform everywhere, and, you know, it changes with time, and then you work out all the, you know, consequences of the Einstein field equations and all of this. Well, the point I wanted to make here in this discussion is that you can do a lot of cosmology without ever thinking of coordinates, without ever writing down a metric. You can do all of this just by playing around with those congruences that we just talked about and those quantities like, you know, expansion, shear, and rotation, and all of this. So, and the idea is that, well, the cosmological fluid, with all of its, you know, the cosmological fluid is an example of a congruence. So it has a vector field u, that's the, you know, the velocity field in the fluid in your cosmology. And it will have a rate of expansion, it will have a shear tensor, and it may have a rotation tensor as well. It has more than that because now we're talking about something substantial. We're talking about real matter, right? So we're back to the fluid dynamics of earlier today. So in addition to having just a bunch of curves and a bunch of geodesics, we're also given, well, a matter density and a mass density and a pressure. So in addition to these quantities, we have the mass density rho and the pressure P. And with that, we can form the energy momentum tensor for the cosmological fluid that has a mass density term in the longitudinal directions and a pressure in the transverse spatial directions. One thing we have to do in cosmology is to postulate an equation of state. So a relationship between the pressure and the density. And typically, what you pick is a linear relationship with a parameter W that turns out to be a constant. So there are a few cases that are particularly relevant. So W is equal to 0. means that the pressure is negligible compared with the density. And that's, that would be the case for a matter-dominated universe where you have a bunch of galaxies or you have cold dark matter for which the pressure is really, negligible. So W equals 0 means P equals 0, and that means matter-dominated universe. Another relevant case is where W is equal to a third. And when you have an equation of state that says that P is a third of the mass density or the energy density, that means that you're dealing with a radiation field. So that would be the case for a radiation-dominated universe. The other one that people, of course, talk about is omega minus 1. And that's an example of dark energy that would be equivalent to a cosmological constant. There are more exotic equations of state that people consider sometimes where W would be even smaller than minus 1. And those are kind of fun because it's, when omega is negative, you actually tend to produce an accelerated universe. If omega is more negative than, if W is more negative than minus 1, the acceleration itself goes nuts, and it actually, the scale factor goes infinite at finite time. So that's a big rip type universe where you generate a final singularity at finite time, and people have played with that in the past. Yeah, and that's about it. So that's the equation of state. When you work out the consequences of energy momentum conservation, it turns out that there are a couple of consequences that come out of this. The first one is an equation that tells you how the mass density will change with time as you follow the congruence. And that's the equation you get. I'm not going to go through those details. Basically, you just plug that energy momentum tensor into the conservation equations, and you isolate the pieces that are orthogonal to U, the pieces that are along U, and that's the piece that's along U, and the piece that's orthogonal to U says that rho plus P du alpha d tau, the acceleration of the fluid, is related to a pressure gradient. So those are the consequences of energy momentum conservation. Now, what we're going to be doing here is to first assume that the fluid moves along geodesics, so I put that equal to 0. And if I put that equal to 0, I'm making the requirement that the pressure has to be uniform inside the fluid. So nothing surprising there. If the pressure is uniform, there are no pressure gradient forces, and therefore there's no acceleration. So this is going to be 0. By assumption, this is 0 also if the assumption is to be consistent. The other equation, this we recognize as our expansion parameter. So one of our first equations here that comes straight out of energy momentum conservation is a relationship between rho and theta. And of course, P can be substituted in favor of rho, so this is something that looks like 1 plus W times rho. So basically, I have one differential equation that relates d rho d tau to rho and theta. And that's one of my cosmological equations. Again, no coordinates, no metrics, and I haven't used Einstein field equations yet. The other equation that I need to complete the picture is going to be an equation that tells me how theta itself evolves. And that's coming from Ray-Chowdhury's equation. So I'm going to keep the discussion simple by putting in a few more assumptions. go up here. So let's build in some additional assumptions. The only assumptions that I've put in so far is that we're dealing with geodesic motion. Right? Apart from that, there's really nothing going on. So of course I've assumed energy momentum conservation, but the only essential assumption that I've made so far is that we're dealing with geodesic motion, and that tells me that the pressure gradient has to be 0. Other than that, there's really nothing into this. Well, there's the assumed form for the equation of state that goes in. So if I list all the assumptions, I'm going to say first that we're assuming geodesic motion. We're also assuming a specific equation of state. But now I want to put in more. I want to assume that our cosmological fluid is not going to shear as it evolves. So I'm going to put in a no shear condition. And I'm going to assume a no rotation condition as well. Why do I do that? Just because. Okay, I'm putting in assumptions that will allow me to simplify the analysis. I'm going to be assuming the Einstein field equations. And that means that the Ricci tensor can be written in terms of the energy momentum tensor. And I have the expression over there for the energy momentum tensor that's built in. As a result of this, I have that R alpha beta, U alpha beta, U alpha, U beta. If I plug in the T alpha beta that I have over here, over there, and I multiply by U alpha, U beta, well, I just multiply by U throughout, and I simplify everything using the normalization condition. I can save a couple of steps of algebra here. What you can quickly show is that you're going to get 4 pi rho plus 3p. So that's coming from the Einstein field equations, and this I can write as 4 pi 1 plus 3w times rho. And now I write Raychaudhuri's equation. Raychaudhuri's equation gives me the minus 1/3 theta squared on the right-hand side. There's no shear term, there's no rotation term, but there's the Ricci term that now has become minus 4 pi 1 plus 3w rho. So what do we have? We have one differential equation for theta. We have one differential equation for rho. And what are the variables? We have rho, we have theta, and w is a fixed constant. So basically, we have as many equations as we have unknowns. And that's a way of doing cosmology without ever writing down a metric. And in fact, you end up with a formulation of cosmology that's very nice because it's essentially, it's a dynamical system, right? 2 first-order differential equations for your 2 fundamental variables, rho and theta. And you can do the usual thing that you would do with dynamical systems. You can represent your flow in phase space and all of this, and identify what the solutions are doing. And it's a very nice way of doing this. This is an approach that, well, is not so much current these days, but in the 70s there was a large effort to understand basically cosmology from a more mathematical perspective. People wanted to understand the impact of putting all those assumptions that you put in when you do FRW cosmology. You make a lot of assumptions there. How much restriction does that imply in terms of the dynamics of your universe? And Ellis and others, George Ellis was probably the main driver for this, said, well, we can do cosmology in a better way by, exploiting Raychaudhuri's equation, and by doing this like this. And of course, they started out by putting all of those assumptions that seem a little bit arbitrary. And they are. I mean, that's just a reflection of, the special nature of our universe as observed. And, there's no reason to not consider other universes that don't have those symmetries. So basically, they started out with, incorporating all of those assumptions, but then they started to relax them one by one. So, first they considered no shear cosmologies, no rotation cosmologies, and then they said, well, let's put in some shear. Let's assume a form for the shear. Let's assume a form for the rotation. So just start relaxing these things and generalize the dynamical system that comes from that and see what you get. And I think it was a fairly fruitful effort that never really interfaced very well with, conventional cosmology because, well, it turns out that FRW was always a pretty good approximation to the real observed universe. But nevertheless, I think as a body of work that sort of clarified a lot of, the stuff about cosmology, I think it was useful. And it's all based on that. Just to tie this up now and finish off the discussion, we haven't talked about the scale factor yet. So I'm coming back to your question. So where's the scale factor? Well, the scale factor is something you can define after the fact. It's not part of this formulation, but you can get it back because we remember that theta is this, right? And I can derive, I can define the scale factor by just saying that my cross-sectional volumes are going to be something that scales as the cube of the scale factor. So I can basically define the scale factor in as follows. I can say that theta, by definition, or the scale factor by definition, is related to theta in this way, which sort of brings out the relationship between cross-sectional volumes very clearly. And if you work it out, of course, you get 3 A dot over A, which means that theta is actually 3 times the Hubble parameter, the A dot over A thing that arises in cosmology. So you can choose to do that. You can choose not to do it. If you choose to do this, then you can rewrite all your equations in terms of A instead of theta, and then you end up with the usual Friedmann equations that you see in your cosmology textbooks. I have nothing wrong with that. There's nothing wrong with that. I'm perfectly pleased with that. But it's sort of fun to think about doing it this way instead in a sort of way that's more tied to really fundamentally what's going on. You have a bunch of time-like geodesics. You have an expansion for the universe, and then you have a rate of expansion for a rate of change for that expansion parameter. And if you push this a little bit more, then you can see as you start playing around with W whether you expect a decelerating universe or an accelerating universe. Clearly, it's going to matter. So if this can be positive, so if W turns out to be a negative, then it's possible for this term to dominate over that term and produce an acceleration in the universe. And it's enough for W to be minus a third in order for that to happen. So for W smaller than minus a third, you have the possibility of an accelerating universe. And if you take W to be all the way down to -1, then easily this term will dominate over that, and you'll get this situation that we seem to have now where the universe is accelerating, that you see right away from here. You have to work a little bit on, so you have to do a bit more work to do all of this to show that it's really how it turns out. But basically, the 2 fundamental equations are here, and that's all you need to do cosmology. All right. Any questions before we quit?
So I think
Yep.
at no stage we used the Einstein equation.
No, we did, right? Because I used it right here to relate the Ricci tensor to the mass density. So here we use them. And well, it turns out to be pretty important for relating, W to deceleration and things like that. Yep. Sure. So typically, what you would do is to say that rho and p have a bunch of terms. So you would say that my cosmological fluid has a matter term, it has a radiation term, and then you can put in whatever you want. You can put in dark matter, you can put in dark energy, you can basically make whatever soup you want for the universe, and then add a bunch of things to the right-hand side and see how all of those things play with each other and what kind of universes you get like that. So if you don't have anything exotic, if W is always positive, then you have two negative signs, and that's guaranteed then that you will get a decelerating universe out of it. So the expectation was that the universe, okay, can be expanding, but it should be decelerating as it expands. That's what everybody believed would be the case up to the mid-90s or so. And then the supernova came along and everything else sort of confirmed it, that, well, in fact, we seem to have an accelerating universe. Makes no sense. But we can reconcile it with the cosmological constant. There's probably a deeper explanation somewhere. People have tried all sorts of things, quintessence, all sorts of, matter fields. You can modify GR and try to do that. I don't think anybody has really put their finger on the right explanation yet. Nevertheless, the observations seem to be holding up, and that's what we're dealing with. All right, other questions? Okay, so next week we'll pick this up again, and I'll probably move to the null case next week.